Okay, so today we're going to talk about some various theorems that are going to help you to solve for the roots of polynomials. We have introduced a couple of these in class already, so just to remind you, one is that every polynomial with complex coefficients in degree n has exactly n roots. So if it's a 4th degree polynomial, it has 4 roots, 5th degree, 5 roots. And also the conjugate root theorem. So if a plus bi is a root, then a minus bi is also a root. So I just want to show you how those can come into play. So take this example. So say I'm asking you to find a cubic equation with integral coefficients that has 2 and 3 minus I as roots. So the first theorem that I showed you would help you say, okay, if it's a cubic equation, that means there's 3 total roots. And they've given you 2, that's one root, and 3 minus I, that's another root. So you just need one more. The conjugate root theorem says that if 3 minus I is the root, then 3 plus I is also a root. Okay, so to form the equation, you take the roots and make the factors. So the factor that goes with 2 would be x minus 2. The factor that goes with 3 minus I would be x minus 3 minus I. And the factor that goes with 3 plus I would be x minus 3 plus I. So that's the reverse. You're given the roots, you turn them into factors, and then you distribute to make the equation, to get the cubic equation. So just some advice, whenever you have imaginary conjugates, so this 3 plus I and 3 minus I, you should FOIL those factors first. That will make the i's disappear more quickly. So let me do that. So x times x is x squared. X times minus 3 plus I, so that's minus x times 3 plus I. And then minus x times 3 minus I. And then this last one, it's minus 3 minus I times minus 3 plus I. The minuses cancel, and it becomes a plus 3 minus I times 3 plus I. All of this you will eventually multiply by that x minus 2 out front. So for now, let's keep dealing with that thing in the brackets. So x squared minus 3x minus ix minus 3x plus ix and then this last foiling, that would be plus 9 plus 3i minus 3i, so that goes away, minus I squared. Okay, so the minus ix and the plus ix go away, and we get x squared minus 6x plus 9 minus I squared. So minus I squared is minus negative 1, so it's like a plus 1. So it's plus 10. So now you just need to FOIL in the x minus 2 into all of that. So you get x cubed minus 6x squared plus 10x minus 2x squared plus 12x minus 20. Leaving you with ultimately x cubed minus 8x squared plus 22x minus 20 equals 0. And that would be your cubic equation. So you could call that f of x. Going from the roots to the factors to the equation itself. Okay, so another Well, let's see. So another example where you could use those theorems would be one like this. Let's say you're given a fourth degree equation. Solve x to the fourth minus 12x minus 5 equals 0. Given one root. So given that negative 1 plus 2i is a root. Okay, well if you know that's a root, then you also know that negative 1 minus 2i is a root by the conjugate root theorem. And since it's a fourth degree polynomial, we have 2, that means we're only missing 2. So those two roots correspond to these two factors, x minus 1 plus 2i, and x minus 1 plus, 1 minus 2i. And you know that there's two other factors that we don't know about right now. We'll call that q of x times those things. And what we're going to do is we're going to ultimately solve for q of x in just a minute. So we start by FOILing those two imaginary terms. X squared minus x times minus 1 minus 2i minus x times minus 1 plus 2i plus minus 1 plus 2i times minus 1 minus 2i. And then get to FOIling, some distribution. So you get a plus x plus 2ix plus x minus 2ix. And then for the very last terms to FOIL, you'll get a plus 1 plus 2i minus 2i minus 4i squared. So a lot of algebra here. These will cancel. Here, I'll draw it. These will cancel. These will cancel. Note that the minus 4i squared is minus 4 times minus 1, or just plus 4. So we get x squared plus 2x plus 1 plus 4. Okay. So what we've done is if you think of this polynomial back up here, let's say that that is something called p of x. We're saying that that thing, p of x, equals q of x times x squared plus 2x plus 5. If we want to find out the other two factors, or the other two roots, we need to factor q. And the easiest way to do that is first to get q, and we'll do that by dividing p of x by the thing that we just obtained. That will give us q of x. And here's where we have to bring in long division again. We'll take our original p of x, that's the x to the fourth, put in your appropriate zeros, so plus 0x cubed plus 0x squared minus 12x minus 5 equals 0. And we'll divide that by x squared plus 2x plus 5. And this is going to give us q of x. So it's just a matter of going through the process. Okay, you multiply the x squared plus 2x plus 5 by x squared. That gives you x to the fourth plus 2x cubed plus 5x squared. Subtract minus 2x cubed minus 5x squared. Bring down the minus 12x. You're going to want to multiply the x squared out front by a minus 2x. That gives you a minus 2x cubed minus 4x squared minus 10x. Subtract those polynomials. The minus 2x cubes cancel. Minus 5x squared plus 4x squared is just minus x squared. Minus 12x minus 10x is just minus 2x. Oops, I wrote too much up here. and then bring down the negative 5, you see, oh, well, we just need to multiply all that by a negative 1 to get minus x squared minus 2x minus 5. And when you subtract those, you get a remainder of 0. So we found our q of x. Q of x equals x squared minus 2x minus 1. Okay, can you just factor it on your own? Turns out that that's actually kind of difficult, and so we return to the quadratic formula. X equals negative b, 2 plus or minus square root b squared minus 4ac, 1 times negative 1, all over 2a. So that is 2 plus or minus root 4 plus 4 over 2. 2 plus or minus root 8, which is just 2 root 2 over 2, or 1 plus or minus root 2. Okay, so here we have the two roots that we were missing, and up here is the one root we were given, and the other root that we figured out with the conjugate root theorem. So now we can say, what are all of our roots? What are all of our solutions to this quartic equation? It will be the set negative 1 plus 2i, negative 1 minus 2i, 1 plus root 2, 1 minus root 2. Or if you want to write that in shorthand, you could say minus 1 plus or minus 2i, and 1 plus or minus root 2. Those four solutions. Okay, so here's a third theorem I'm going to give you, something that you've definitely seen in Algebra 2. So if you would write this down, it's called Descartes' rule of signs. I'll read it, and if you need to pause it so you can write it down, feel free to. But let p of x be a polynomial with real coefficients in terms arranged in decreasing degree of x. So, put the x to the fourth first, and then the x to the third, and the x squared. Then, 1, the number of positive real roots of p of x equals 0 is equal to the number of variations in sign of p of x, or is fewer than that number by an even integer. Yeah, that says even integer. And then 2, the number of negative real roots of p of x equals 0 is equals the number of variations in sign of p of negative x. So that's a difference here. P of x versus p of negative x, or is fewer than this number by an even integer. So pause if you need to write this down. So you have seen this in Algebra 2. So I'm going to help you remember what you've learned about this. So let's look at an example to flesh it out. Let's say you're given p of x is equal to x to the 6th minus 2x to the 4th minus 5x squared plus 3x minus 6. We want to know what are the possibilities for positive or negative real roots. So we first look at p of x, see how many sign changes there are. I see one sign change, second sign change, third sign change. That means there are 3 or less than 3 by an even integer, so 2 is a number less than 3, so 3 minus 2, 3 or 1 positive real roots. If we want to find out how many possible negative real roots, we would need to plug in negative x, and so all the even exponents will stay the same because negative x to an even exponent, the negative will just go away. But we'll change all the odd exponents. So p of negative x would be negative x to the 6th, or just x to the 6th, minus 2 times negative x to the fourth, which would just still be x to the fourth, minus 5x squared, plus 3 times negative x, which would be minus 3x, minus 6. So we see, okay, one sign change, and then the rest of the signs are negative, so that tells us there's only one negative real root. So the interesting thing is we know it's a 6th-degree equation. So we know it's a 6th-degree polynomial, so that means there's 6 roots, but some of them can be imaginary. So we could make a table for the positive real roots, the negative real roots, negative real roots, and then the imaginary roots, not real roots. And we say, okay, we said we could have 3 or 1 positive real roots. So that's our 2 possible outcomes, 3 or 1 positive real roots. And there's only 1 negative real root. Because we can't subtract 2 off of 1 and say we have, negative 1 negative real roots. That doesn't make any sense. So there's only 1 negative real root. And if we have to have a total of 6 roots, that means for the first row here, 3 positive real, 1 negative real, we'd have to have 2 imaginary roots to get 6 total. And if we had 1 positive and 1 negative, we'd have to have 4 imaginary roots. So this helps us, see what the possibilities are for the kinds of roots we'll get. So here's an example which I'd like you to try on your own. Example 4, list the possibilities for the nature of the roots of p of x if p of x equals 5x to the fourth minus 3x squared plus 6x minus 10. So you try and do that one first, so pause it and then check your answer once you've tried it. So it looks like we have 1 sign change, 2, 3. So there's 3 or 1 positive real roots. And if we do p of negative x, that'd be 5x to the fourth minus 3x squared minus 6x minus 10. So this is just like the last problem actually. Oops, sorry. There's only 1 sign change there. So that'd be only 1 negative real root. Okay, and it's a 4th-degree polynomial, so there's 4 total roots. So we can make a table, the positive real roots, the negative real, the imaginary roots. Well, 3 or 1 positive. We've definitely got 1 negative. If there's a total of 4, then there's 0 imaginary in this case, and 2 imaginary in this case. So that'll wrap up this video. Please find the following video to learn about the rational root theorem and how that helps us to solve for the roots of an equation.